can we go bigger? Right? That's always the interview tactic, right? Is that the best you can do? And so the answer here is no. I think we can do even better. But we're going to have to switch tactics one more time. And in order to switch tactics, we have to explore some elements of matrices.
Our next guest is a guest from so far away. It's Kyle, and he'll talk about the Fibonacci Funhouse, right? Cool. Let's give him a warm welcome.
Thanks, everyone, for actively choosing to be at my talk today. I know you didn't really have a choice. This is my talk. I've called it the Fibonacci Funhouse. And I'm a pretty big math nerd. I really like algorithms, and I really like Ruby. And so I thought this would be an awesome way to combine all three of these things into this special talk today. And the goal of this talk is to showcase some of the interesting things that we can do in Ruby by walking through various algorithms for finding Fibonacci numbers. A little bit about myself. My name is Kyle D'Oliveira. I'm a principal software engineer based out of Vancouver, British Columbia, Canada, so quite some far away from here. I've been working with Ruby for over 15 years. I've worked with some really large, really complex code bases, but I've stayed in the Ruby world because I really love the Ruby community, and you are all a great example of that community. And I foresee myself staying with the Ruby community because of you all. Just a quick shout out to the place that I work. I work for AHA, which I have worked there for the last 4 years. And it's one of the best workplaces that I have been a part of. We provide tools to help other companies build what matter to them with our suite of products. And it's an amazing team that's fully distributed all over the world. We don't have an office anywhere. It's got one of the best company cultures that I've ever experienced. And we are powered by TRM, the responsive method, which is just a way of giving us all shared values that we can all make decisions that we can agree on, we can embody these values, and it just empowers us to move forward, stay aligned. And if you want to be part of this, come talk to me at some point during this conference. And when I was beginning to plan this talk, I was thinking of various ways that I could tell it. And one way that I thought would be really interesting is to go through this as if I was being prodded by an interviewer. Because we've all seen or heard about the interview questions like, can you write a Fibonacci algorithm? So if you ever have that in the future, this talk will give you all of the answers you need to answer that interview question perfectly. So here is my helpful interviewer today, and we're going to go through various Fibonacci algorithms. And so first, we have to start with the really, really basic question, which is going to start with, what are the Fibonacci numbers? And can I write any method to give me a Fibonacci number? Well, the Fibonacci sequence is just a sequence of numbers where each number is the sum of the previous two. So here's a list of the first several. We can see like 5 plus 8 is 13, 8 plus 13 is 21, and so forth. This is an infinite sequence. You can always look for bigger numbers. You can also visually represent this with these little squares. You could say each Fibonacci number is a square that's the sum of the two previous squares. So you can kind of end up with these squares that kind of get bigger and bigger, and this represents this kind of spiral. And you may notice this. This is often referred to as the golden spiral. I even have part of it tattooed on my arm. That's how much you can see I'm a bit of a math nerd. So let's get to writing some algorithms. We can write a really basic algorithm that looks just like this. We can define a method called Fibonacci. We can define some base cases, just like our definition. And then we can just simply sum up the previous two numbers. I would wager that all of you have seen this method before in some form or another. But if you ever wrote this in an interview, you'd be prompted to be like, well, what does the performance of this look like? Is this a good method or not? So we might want to look at the performance, and if we have a graph where the x-axis is what Fibonacci number we're looking for in the sequence, and the y is our time, it's okay, and then it gets really, really bad. And yeah, it's no surprise that it gets really bad, but the question would be, why does this get so bad? And if you think about how it looks to build out the Fibonacci numbers, if you wanted to calculate the fifth Fibonacci, for instance, in order to calculate that, you kind of need the fourth and the third. In order to calculate the fourth, you need the third and the second. The third needs the second and the first. The second needs the first and zeroth, and so forth. And what we can kind of see, there are whole sections of this tree that are repeated. And as we are looking for larger and larger numbers with this algorithm, more and more of this tree is going to repeat, leading to an exponential growth in the amount of calculations that we're going to do. So if we were in an interview, we'd probably be prompted at this point in time to find a more efficient manner to do this. How could we find the 100th number in the sequence if this started getting bad around 30? Well, we're all clever. We can look up information on Wikipedia, and we often hear that there is a formula for this, so we'll just start directly there. And so this formula is referred to as Binet's formula, and it looks like this, which seems very complicated. The f of n here represents the nth Fibonacci number, and then we've got these special numbers. This one's called phi, which is defined by 1 plus the square root of 5 over 2. Lots of numbers. The other one is often referred to is called psi, which is the same thing with minus, so it's 1 minus the square root of 5 over 2. These two numbers are very related. They're reciprocals of each other. They're also 1 less. We can also simplify this formula a little bit to something that looks like this, a little bit simpler. Basically saying the nth Fibonacci number is the closest number to phi raised to the power n divided by the square root of 5. So with that, we could write another algorithm in Ruby. We can say, here's the square root of 5. We can define this value phi, which is as defined by 1 plus the square root of 5 over 2. And then we can literally just have our algorithm. We can define it like this. Raise phi to the power n, square root of 5, find the closest number, and there we go. We've got our Fibonacci formula. And so if this is our old graph, where it started getting bad around 30, this is our new one, which is constant time, right? This is the holy grail of all algorithms, right? Constant time, never gets worse. But there's some problems. And one of the problems here is that when we get to 1,475, it just full on errors. You get an error in the float domain error. And this happens when Ruby tries to take a number and it gets too big for it to represent, and it just gives up and it says it's infinity. And when you try to round infinity, you get a float domain error. And so at this point in time, if you take that special constant phi and you try to raise it to the power of 1,475, you get infinity, which doesn't seem correct, but Ruby thinks it is. There's also a second problem here, which is that we only have a limited amount of precision. So around 71, you get this value here, which is too big for me to actually say. But the actual Fibonacci number is just 1 less than this. And as we're looking for bigger and bigger Fibonacci numbers, this difference is just going to get larger and larger. So we need to do something different. But this is where Ruby's strengths start to really show. Ruby has a library built into it already called Big Decimal. And it provides arbitrary precision floating point decimal arithmetic, which is a bit of a mouthful. But you can tell it how much precision you want to have, and it's a great library to have if you want to start avoiding these rounding errors due to precision. And so we can quickly rewrite our algorithm that we had by doing something like this. Instead of using the math library in Ruby, we can get the big decimal representation of 5 and take the square root of that to 1,000 decimal points, or 1,000 points of precision. And then the rest of the algorithm looks exactly the same. And that's great. What does our algorithm look like in terms of performance? If this was our basic algorithm, we no longer have a constant time algorithm for finding it, but we do get more than what we had previously. And this is because we have to do a lot more work to create this additional precision, so we have to do more processing power, and as we get larger and larger numbers, it's going to be a little bit slower each time. And so when we get to around 350 or so on my machine, it started crossing like the 3.5 second barrier, and it's just steadily gets worse and worse as we go. But Big Decimal is a really great library to have. So although it's slower than a lot of the Ruby standard numeric operations, it avoids a lot of the precision pitfalls that you run into. So if you need to avoid those precision pitfalls, this is a great tool to have in your back pocket. Okay, so back to the probing interview questions, right? Well, we got to 350, 400. Can we get to 1,000? Well, I think we can get better, but we're going to have to change tactics just a little bit. So let's think about it in terms of rationals instead of decimals. So Ruby has actually really good support for rationals as well. And it's a lot easier for Ruby to work with rational numbers because then it just works with the standard numeric representations of the numerator and the denominator. And luckily for us, there is this really complex looking piece here, which is a representation of the square root of 5 as this continued fraction. It's an irrational number, so by definition, there is no fixed rational number for it. But what we can do is we can create an approximation. And if we think about the square root of 5, which is this number up here, this 2.23606, so forth. If we took that repeating rational and did it to a couple levels, we get 13 over 17, which is an okay representation of it. We go one level deeper, which is 161 over 72, which gets a little bit better. And we keep going this. We can keep doing this over and over and over and get better and better approximations of this square root of 5. So let's come back to our formula. We can create a new formula by saying, like, hey, we're going to go 1,000 levels deep in this fraction. And then we can create our representation of the square root of 5 by going 2 plus how many times we want to do this, and we build out this continued fraction using Ruby's support for rational numbers. And then the rest of the algorithm stays exactly the same. We can define our constant phi by these values, and then raise to the power n, divide by square root of 5. And this is actually kind of cool. This actually has some pretty massive differences. This is the performance impact of the Big Decimal version, and that's the version with rationals. So we can get much, much farther using rational numbers than we can with decimals. But this also still has problems. As you may have guessed, because we're working with an approximation, at some point we're going to start getting wrong values. And for this, it's about 5,994. The numbers start getting wrong. Now, that's not great. We're trying to get correct numbers. That's the whole point of the algorithm. And you'd think, hey, we can just increase how far we go down in this approximation so we could get even better approximation. But eventually, at some point, we get our friend float domain error. And this is because the numerator and the denominators have gotten so large that when you raise them to an exponent, Ruby just gives up and says, that's too big, that's probably infinity, which I think is wrong every time, but that's what it does. So rational numbers are actually a really, really good way of finding the balance between performance and precision. And so if you have data that can be represented as a rational number and you need to avoid precision, representing it this way within Ruby is really good. And so it's a good tool to just have in your back pocket to be able to use it. Okay, so we're going to keep prompting. We got to like 6,000. Can we get to 10,000? So I think this is the best I can do in terms of a formula. So let's go back to the basics and try a very different approach. Remember, the problem that we had with the original algorithm was that we were just doing way too much work, lots of duplicate work. So instead of doing it like this, we could create a recursive function that sums up the values and decrements n on each call, and that way we could reduce a lot of duplicated effort. So we could write a method that looks like this, where we pass in some default parameters, we've got some base cases, and then we just have a single recursive line. And so n goes down, b and a go up, and this will give you the Fibonacci number for whatever you like. And this already is quite good. We can get well past any of the formulas that we had, get to, on my machine, about 8,720, but then we're going to hit something called a system stack error. And I'm sure some of you have seen something like this before. And what's really happening here is that for each method call on our stack, we're adding a new caller on onto our stack, and we continue to go down. So 4 calls 3, calls 2, calls 1. And if we're done, Ruby just comes right back up, gives us the answer. But if this stack gets so large that it can get so large that Ruby has to make a call. It says, is this intentional, or are you just going to recurse forever? And at some point, Ruby has to make a decision, and my machine, about 8,700 recursive calls, it says, I think you're going to repeat forever. This is an error. We get the system stack error, and it aborts. But there's an interesting feature that is supported by Ruby that we don't see very often, and this is something called tail call optimization. And it can help with these large stacks. So this is our original algorithm, and what tail call optimization does is if the last method or the last line of a method is a recursive call to itself, and that's it, we can use a tail call. In this case, we couldn't use a tail call because even though the last line looks like it's a recursive call, there's 2 recursive calls, so it doesn't quite work. But our recursive version does have this property where the last line is a recursive call to itself. And what tail call optimization does, if we looked at that same kind of call stack, instead of adding a new one, conceptually, it's just going to replace the existing one and say, okay, instead of adding a new caller to this, we're just going to replace that with the one for 4. And then if that one calls something, we're going to just replace that with the one for 3, and so forth. And what ends up happening here is the call stack remains constant the whole time. So you can recurse forever, and Ruby will never give you that system stack error. In Ruby, this is off by default, but we can instruct the Ruby compiler to enable it. So firstly, you could just define your recursive function in a file, such as this Fibonacci.rb. And then what you could do is just add this piece of code where you tell the Ruby VM the instruction sequence to enable tail call optimization and disabling trace instruction. And then when you include that file, this method will be tail call optimized. And this has some really interesting performance optimizations for our Fibonacci algorithms. So this is our old best. We're getting to about 6,000 or so with our rational formula. And this is the corresponding one with the tail call optimization, where not only are we able to get to 10,000, we can easily pass 100,000, get all the way up to 500,000 in relatively short order. That's pretty cool. Tail call optimization, really neat. It's a very tricky feature. It can be really useful, can be really powerful if you've got a recursive method that's doing some, that fits the parameters of this where the last line calls itself. But it is also quite hard to use. It's hard to see and confirm that it is using tail call optimization. It won't complain if it's not until you hit the system stack error. So it's easy to accidentally disable it and not notice it. And it can make debugging a little bit trickier, but this is an interesting feature of the language that I didn't know existed until I started playing with it. Okay. Being prompted, poked further, can we go bigger? Right? That's always the interview tactic, right? Is that the best you can do? And so the answer here is no. I think we can do even better. But we're going to have to switch tactics one more time. And in order to switch tactics, we have to explore some elements of matrices. And matrices is a concept from math, where it's just an array of numbers. So this is a 2x3 matrix, just representing 6 elements. And matrices in math have very specific operations for addition and multiplication. And the multiplication is kind of weird. If you multiply 2 matrices together, the result is like the first element in the row times the first element in the column plus the second element in the row, then the second element in the column. It kind of does this diagonal or this across and down thing at the same time, and then it's all the permutations of that. It's a little bit complicated, but it is well defined. But this fact is important because there is another identity for Fibonacci numbers that involve matrices. If you have this special 2x2 matrix with these 3 ones and a 0, and you raise that to the nth power, you give a matrix that has the n plus first and 2 copies of the nth and 1 copy of the n minus 1th Fibonacci number. And that's pretty neat. It's kind of unexpected, but pretty neat. And we can actually see how this would work together. Like in particular, if we looked at an example, if we took the n minus first matrix, multiplied it by the this like 3 1s and a 0 matrix, we can kind of get this over here, because if we start looking at this, we see, the first row, first column, that's f of n, and then it's like n minus 1, and then we can see f of n's over here, and anything times 0 is 0, and we can kind of go through all of the pieces to kind of see how this would be constructed. We've got the n minus 1 here, and then of course anything times 0 doesn't show up. And then the matrix on the right can just be simplified over to this. So we can see how we can build higher and higher of these like Fibonacci matrices, which is kind of neat. But now we have a new algorithm that we could leverage to explore Fibonacci numbers. And so we can write our matrix multiplication algorithm. And Ruby has good support for matrices already. We don't have to do all this kind of weird behavior. We can just literally make a matrix representation in Ruby. And then we can just define our Fibonacci algorithm very similar, where we have our base cases. And then we're just n times, we're just going to multiply this to itself. And we're just going to build this up, and we're going to return the value that's in the top right. So that's pretty cool. What does this look like in terms of performance? So here is our old best, our tail recursion, and this would be our matrix multiplication. It's actually much worse. But while this is slower, there's some interesting things you can do with matrices that can make this much better. So instead of doing this multiplication n times, we can do much less. And this is a property of matrices. So if we're looking for something like the 11th Fibonacci number, we could take this special matrix and raise it to the power of 11. But also, we know that 11 is just 8 plus 2 plus 1. Well, a property of matrix multiplication is if you have something that looks like this, you can split it up into individual matrices multiplied to that, all multiplied together. And if you just manually expanded that out, you get this. And if you bring it all together, we can see that the 11th Fibonacci number is 89. Well, it's kind of weird, but really cool. Nice things that we can do in math. But this gives us a new algorithm that we can explore. And this is often referred to as the repeated squares algorithm. So we can define our Fibonacci matrix, this special matrix here. And then this algorithm is going to be a little bit more complicated. We set up our method definition. We can set this result to the identity matrix, which is just the equivalent of like 1 for multiplication. We can set our base to be this Fibonacci matrix. And then we have this loop. And we're going to loop through this. And we can look at the individual pieces of n, how big our number is. We can say if the last digit is 1, basically saying if it's odd, we can increase the base. Otherwise, we square the base. And then we shrink n, and then we return the value in the top. This is a little bit more complicated, and it might seem unclear, so I'm going to go through this with a little example. The example looks like, imagine that we were given this value of n being 11, and we can see the binary representation of 11 as 1, 0, 1, 1. So we can set up our result n base, and there's our identity matrix and our Fibonacci matrix, our special matrix there. And then we can say, is the last bit of this 1? If it is, we update the result. Then we square our base, and then we shift all the bits of n over 1. And so now n becomes 5, and here's the binary representation of that. Well, we can see that the last digit is still 1, so we can update the result. We can square our base, and we can bit shift it 1 more over. The last digit is not 1, so we just square our base. We shift it 1 more over, and now we see, like, for the last piece, the last digit is 1, so we update our algorithm, and we return 89. That is the 11th Fibonacci number. And this is pretty cool. So now there is our tail recursion, which was our best. And now we can get into the millions. We can get 45 million pretty easily in just a couple seconds. But this is just to highlight some of these interesting things you can do with bitwise operators in Ruby. And I think this is actually a really cool tool to just have in your tool belt. Obviously, sometimes dividing by 2 and using like the integer division makes more sense than bit shifting and is a little bit more readable. So maybe for some math purposes, you'd want to stay on the side of readability, but doing bitwise ANDing and ORing or shifting bits is actually a really useful trick to do various things. You can create random numbers that also have pieces of the time built into it by bit shifting the time over. Or you could create a configuration value of a bunch of Booleans and store them as a single value and just look at the individual bits to see if they are on or off. And you can use ORing or ANDing to set or clear them. Okay, one more time. Coming back to the interview question, continuing to be prodded, is this the best we can do? No. I think we can go more. I think we can keep going more. So there's one last thing we can do. If you think about this matrix calculation, we're doing a lot of redundant calculations. We are actually creating 4 Fibonacci numbers all at the same time, and we're doing a lot of operations to create those. So there's a simpler way of representing this. And one more time down the layer of math, if we were to look at this matrix for the 2nth Fibonacci number, we have, based off our identity, it could be represented like this. But this is also something we can do with matrix algebra, as we could represent this as the nth Fibonacci matrix squared. So it would look like that, and if we just manually expand it out, we get this mess, and if we simplified it, we get that. And this is really complicated, but the important thing is these two, the thing at the top left and the thing in the bottom right, are the same. So we have a representation of odd Fibonacci numbers, and we have a representation of even Fibonacci numbers. And both of them are defined by basically values that are roughly 1/2 of it. So this is really cool. So now we can get to the last algorithm here, which is often referred to as fast doubling. And I'm going to split this into 2 pieces here. So firstly, to prevent some redundant calculations, I'm going to do the first piece. And we're going to do this inside of a default proc of a hash. So we can create a new hash here, and we can say if we enter this default block, basically saying where we hit a key that doesn't exist yet in this hash, we're going to run this _fib method, and we're going to calculate some stuff. And the stuff will come in just a moment. But then with this default hash, we can set some values that we know. This is our base cases. We can set 0, 1, and 2. And then we can just ask it, what is our nth one? And this would give us our Fibonacci number if this _fib worked. And what that method would look like is we can say, hey, we've got like a hash that we're going to store some things on, do some dynamic programming. We can get the value that is 1/2 of n, we'll call it half n. We can extract the value that is half n plus 1 and half of n. And then remember, we have these 2 formulas. So if it's odd, we do this. So we can do something like this. If n is odd, go a times a plus b times b. Now, this is also important that a times a in Ruby technically is not the same as a squared. Because when numbers get too big, Ruby will give up and just tell you it's infinity. So a times a is not quite the same, so we'll do it that way. And then we have a representation of even Fibonacci numbers, which look like that. So we say 2 times a times b minus b times b. There we go. So now we can take our Fibonacci algorithm, and here is our repeated squares, and now that is poor, and we can get into the 450 millions. We can actually just keep going. This is pretty easy, and some of this is due to this hash default procs, which is a really, really useful thing to just have in your back pocket all the time. Lets you do things on a hash if keys don't exist. Really interesting way to do some dynamic programming, to do memoization. I've used this many times to create like a lazily created hash of hashes, so you could do some configuration options that way. Super useful tool to have in your toolbox. And because we often talk about like Ruby at scale, it's like, can we find the billionth Fibonacci number? Yeah, we can. It's actually pretty easy. Using this algorithm, we could find this in about 10 seconds. It's way too big to put on the slide. It's 208 million digits long. So that's really, really big. But this is faster than any C algorithm that exists, at least in the same comparison on my computer. So when people ask, is Ruby fast for computation? The answer often here is like, yes. Yes, it is. And I think that point, that's the best I can do. I hope you all learned something interesting that you can do in Ruby. Stuff this stuff in your toolbox so that you can do some interesting operations. And if anyone ever asks you in an interview about Fibonacci numbers, you can probably take over the entire interview, get all the way up to 1 billion, and they probably won't ask you any further questions. Thank you.